guys. So the other day, the last couple of weeks, we've been working with Euler paths and Euler circuits, right? What we're going to be working with today is we're going to be working with something called Hamiltonian paths and Hamiltonian circuits. Hamiltonian path circuits, do that here, Hamiltonian circuits, and Hamiltonian paths. And again, it's the good thing is you guys have already gotten the hang of it. This is going to be a little bit different in the way that where we were able to calculate degrees before to see if it was an Euler path or an Euler circuit. This way with this we can't. So first and foremost, right, when it comes to a Hamiltonian circuit and a Hamiltonian path, the reason that it's different from the Euler paths and the Euler circuits is because when it came to Euler paths and Euler circuits, your goal was to connect all the edges exactly once, right? So when it comes to connecting edges, that's an Euler graph, right? When it comes to Hamiltonian paths, the difference between this is we are just trying to connect vertices instead. So if we have this, right? If we have this, all this is again, it would just be a case of a Hamiltonian path, Hamiltonian circuit. Because again, when it comes to a Hamiltonian path and a Hamiltonian circuit, Hamiltonian just tells us that you're just using the edges, just using the vertices, I'm sorry. Each one uses the vertices, uses vertices for both, only once. All it is, guys, for both of these, whether it's a Hamiltonian circuit or a Hamiltonian path, it's going to use vertices only once. That's it. You can't ever repeat a vertex, right? That's why I wrote it across, because it does apply to both. But now when we're looking at that, is the important part is we need to actually see what makes them different from each other, right? So you guys know the difference between circuits and paths because you did well with it on the quiz and we actually explained it. Circuits always finish where they start, right? It ends at the vertex where it started. A path ends at a different point than where it started. So what you have to understand about Hamiltonian paths and Hamiltonian circuits, it doesn't necessarily have to use every single edge because you're not concerned about the edges so much anymore. You need to just make sure that you use each vertex, each point, exactly one time. Like for example, if I were to look at this point right here, and again, since it's a circuit, we have to finish where we started. When it comes to that, what we're going to do is, again, we're moving from this point, and now for Hamiltonian circuits, we have to connect all vertices together, right? So if I go here, I connect it to this point. I go here, I connect it to this point, because I'm actually following the path too. Over here, I connect it to this point. I connect it to this point, and then I connect it back to the point where I started. That's why that's a Hamiltonian circuit, because we literally connected all the vertices and we finished at where we started. That's why it's a Hamiltonian. And again, there's no way of calculating degrees because for this, you actually have to just work with it. You have to trace it, you have to draw it, you actually have to be able to see if you can connect everything without lifting up your pen or your pencil, all of that. You can never lift it up. You always have to trace along a path that's there, any path. Doesn't have to use all the edges, but again, it's just connecting all the vertices once. You can't ever repeat it other than the one where you finished, right? So the only time you can ever have a vertex that you actually see again is when you actually go back to where you started. This one over here, we know that since it's a path, it ends somewhere differently than where it started, right? So again, since it's a Hamiltonian path, we're just connecting the vertices, right? So we have our starting point here. We go here, right? We connected that vertex. We go here, connected this vertex. We go here, we connected this vertex. And we go here, we connected this vertex. Now the important part is, again, even though we didn't use all the edges, it doesn't matter because that's not our goal. Our goal for a Hamiltonian path or Hamiltonian circuit is to connect just all the vertices, right? All the points, and we did. We connected this, we connected that. But now that's the problem. The reason why it's not a circuit is we can't go back to where we started. Because if I were to go back, now I would go back this way, but there's the problem. Since I already used that point, I can't repeat it. Since I can't repeat it and I can't get back here, this is why that's a path. It's a path because literally we finished somewhere than where we started. Always remember, guys, when it comes to a Hamiltonian path or Hamiltonian circuit, you can't ever go back. Because the second you repeat, automatically that's no longer Hamiltonian anything. You cannot repeat the vertices. But again, Hamiltonian circuit, Hamiltonian path, you have to connect all the points exactly once. You can't ever repeat. So again, it's easier to see in just that you guys are used to it. It's easier to focus just on the vertices, the points, as opposed to focusing on the edges. But again, there's no easy way to actually do this in terms of calculating degrees. It's just you having to practice, right? So let's say now that I wanted to figure out if these things represent Hamiltonian circuits, Hamiltonian paths, or neither. All it is, it's just practicing, guys, right? So let's say I created this vertex edge graph, right? Where I have this, right? And I want to see which one it is. Again, there is no easy way to actually be able to do this, guys. And again, I'm showing you some of these again just because we have worked with these before. But I do want to show you that just because it wasn't an Euler circuit or an Euler path doesn't necessarily mean it's also not going to be a Hamiltonian circuit or path. They have nothing to do with each other in some regards. So now again, we want to see if this is going to represent a Hamiltonian path, a Hamiltonian circuit, or neither, right? And again, pick any point. Again, when you pick a point, our goal is to go to every vertex once and then end at where it started. If we can end at where we started, that's a circuit. If we can't end at where we started, we end at some other point, that's a path. And if we can't connect all the vertices, it's neither, right? So we start here, let's go here, right? We connect that. Let's go here, we connected that, right? Let's go here, we connected that. And there's not just one way, guys. Go here, we connected that, right? We go here, we connected this one. And now the good thing is we can actually go back to where we started. And since we connected every single vertex and went back to where we started, this would be considered a Hamiltonian circuit, right? And it's a Hamiltonian circuit for that exact reason. It's we ended up going back to where we started and we used each vertex once. Since we used each vertex once and ended where we started, that's a Hamiltonian circuit, right? It's just that idea, guys. If I now were to do, let's say I were to give you guys here. Let's say I were to give you guys this, right? It's just this idea right there. If I had this, right? Where we have this vertex edge graph, same idea, guys. It's can we actually connect everything, all the vertices, whether we go back to where we started or whether we end at a different point, that's our goal, right? So again, picking any point, right? Let's say I pick this point, and again, it's not whether it's possible from the point that you start at, it's whether you can do it from any point regardless, right? So if it doesn't work for this, it doesn't necessarily mean that it's not a Hamiltonian path or a Hamiltonian circuit. Sometimes it's okay to play with different points to see if it works. I picked this one here because again, it's just seeing it. I know I start there, I go to this point, 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 right? Now be careful because again, we connected all of them so far, but there's no way for me to connect this to this directly. So I would have to go back this way, but if I were to go back this way, there's our problem because I already used that. Can't use it again. So since I can't use it again, I'm ending at a different point than where I started. So automatically we know it's going to be a Hamiltonian path, right? And we know it's a Hamiltonian path again because we finished at a different point than where we started. We finished there, we started here, and we used each vertex, each point only got used once. That's why it's a Hamiltonian path. And then again, I'll do one more just for you guys to see. for the last one here, again, let's say I were to look at this, and it's always just trying to figure out whether you can actually do it. We have that, right? We have this right here. We have this, we have that. Then let's say I had this here as well, right? I want to figure out if this is a Hamiltonian path, a Hamiltonian circuit, or neither. Same idea, guys. Pick a point, right? Try to play with it. See if you can actually get it. Again, I usually try to start with the farthest point away. I start here, right? I connect it to this vertex. And now here's the problem. Starting here, some people may go here, there, and then say it's not possible. Try to connect it, you know what I mean? I know I can go here because they're connected. I know I can go here because they're connected. I know I can go here because they're connected. So again, we used all 5 of them, but now we can't go back to where we started because they're not connected. And if I were to go backwards, I'd repeat. Don't ever want to repeat. Since I finished at a different point than where I started, it'd be a Hamiltonian path. And again, guys, it's just practicing with this to be able to see whether you can or can't. Sometimes they're possible, sometimes they're not, okay? But any questions, feel free to ask, guys.